Okay, so we're going to be looking at lesson 7-6, but to reward those of you who are watching these videos, I'm going to give you a little fun here. So, here is a question that will be answered at the end of this lesson. The question is, what do you get when you cross a pencil with a hot dog? What do you get when you cross a pencil with a hot dog? Answer forthcoming. This lesson and the last lesson, 7-6 and 7-7, are both going to look at applications of exponential functions. So, exponential functions are used to model situations where the dependent variable changes, increases, or decreases by a constant factor for each one unit change in the independent variable. So here's our first example. Upon graduating from college, Ashley took a job with a starting salary of $40,000, and she can expect a 6% raise in pay each year. Compute her salary for the first 4 years. So, for year 2, I know that we're going to take 40,000, and we're going to multiply that times that 6% written as a decimal would be 0.06, so that would be the amount of her raise, and we'll add that to the 40,000 she's making. So if I factor out that 40,000, it's basically 40,000 times 1 plus 0.06, 1.06 times 40,000, and that will give us her first year salary, well, at the end of her first year, of $42,400. Next year's salary, we could take the $42,400, the salary at the end of her first year, and multiply that times 1.06. But notice that that's going to be the same as this 42,400, remember, was 40,000 times 1.06. And then we're going to multiply that times the 1.06 again, or 40,000 times 1.06 squared. And we are getting for that one 44,944. So I've got 40,000 times 1.06, 40,000 times 1.06 squared for the second year. Into the third year then, we'll have 40,000 times, I hope you see the pattern here, 1.06 to the third. And that gives us $47,000, $640.64. And then at the end of the fourth year, 40,000 times 1.06 to the fourth. And this one we're going to round to the nearest penny since we're talking about money. $50,499.08. So write a function for Ashley's salary after T years. Be 40,000 times 1.06 to the T power. Okay, so we're graphing this function now. So we're going to use our handy-dandy calculators here. So I've typed into the y equals screen 40,000 times 1.06 to the x power. It says 0 to 30 years, so in my window, my x min is 0, my x max is 30. And just having fiddled with it a little bit, I know the y min, it's not going to go below 0 clearly because she's going to start at 40,000. And I figured out that a pretty good window is going to be 250,000 for the max. I know that just after 4 years she's making over 50,000, but after 30 years she's going to be making pretty good money here. So if I graph that, I get something that looks like this. Okay, so just trying to get some read on that. I know it's starting at 40,000. So determine Ashley's salary after 10 years, 20 years. We can easily do that with our calculator by using second trace 1. So I'm going to put in 10 for x, and I get a salary of, and I'm going to, again, rounding this to the nearest penny, $71,633.91. 20 years, I don't have to hit second trace 1 again. I can just hit 20. Press enter. I've got $128,285.42. And then the last question says, when will Ashley earn $60,000? Clearly it's before 10 years, because in 10 years she'll be earning over 70. The only way we can have to solve this right now is graphically. So I'm going to go back to the y equals screen. For y2, I'm going to put in 60,000. And we'll see this red line, 60,000. And what I want to find is this point of intersection right here. So I'm going to hit second, trace, and this time I want intersect, number 5. The cursor's right in the middle, so I'm going to move my cursor down. It's asking me for first curve, but I'm just going to if you put the cursor near to your point of intersection, then I'm just going to hit first curve, enter, second curve, enter, guess, enter one more time, and the answer is my intersection happens at x equals 6.959 years. 6.959 years, and that was again rounded. It was 6.9585, so I'm rounding up to 6.959 years. Okay? So that first problem dealing with Ashley was an example of an exponential growth problem. She had a beginning salary of $40,000. It is growing at 6% per year. It's adding on 6% per year. So here's our general form of an exponential growth model. A of t is equal to a sub 0 times b to the t power. We're going to see this a sub 0 a lot. And the a sub 0 stands for the amount at t equals 0, also called your initial amount, your beginning amount, how much you're starting at. A of t is going to be your amount at time t. Your b, your base, is your 1 plus your r, 1 minus your r. If it's growth, it'll be 1 plus r. And this, like with Ashley, 1 plus 6%, 1.06. This next problem we're going to look at is going to be, the rate's going to be decreasing. It'll be 1 minus r here. R is your rate of change, and then t is going to be time. So let's look at this second example. If you drank one soft drink, the formula for the amount of caffeine in milligrams left in your body after t hours would be A of t is equal to 100 times 0.86 to the t power. Notice our b value here is less than 1, so this is a decreasing function. It is a decay. It's a decay function. And so as time goes on, it's going to be less and less and less. So what's the initial amount of caffeine? Well, the initial amount, if I put in 0, 100 times 0.86 to the 0 power, anything to the 0 power, 0.86 to the 0 power is 1. 100 times 1, it's going to be 100, and we're talking about milligrams here. So 100 milligrams is what we started with, and that's also clear just from the formula itself. A sub 0 is 100. What is the rate of change as a percent? Well, our rate of change is b is our factor, and so I'm going to say 0.86 equals 1 plus r or minus r, but if I solve this, if I subtract 1 from both sides, then I get r is equal to 0.86 minus 1, which is a negative 0.14. Changing that to a percent would be negative 14%. We are losing 14% every hour. Okay? We're losing 14% of the caffeine every hour. How much caffeine is in the body after 5 hours? Well, go to my calculator here, and we're going to put in 100. Let me just clear all this stuff out. 100 times 0.86 to the 5th power. And when I do that, I get 47.043. 100 times 0.86 to the 5th power is 47.043 milligrams. After 5 hours, about a little over half of the caffeine has left the body. All right, so we're looking at part D. When will the amount of caffeine in the body be less than 10 milligrams? So we're going to need to use the graphing calculator for this. So I put my original function in at y1, 100 times 0.86 to the x power. I set my window from 0 to 20, so we're going to look at the first 20 hours, 0 to 20, x max is 20, x min is 0. I went a little bit higher for my y max than 100 because I know that's going to be my maximum level, because at time 0 I'm at 100, it'll decrease from there. But I went a little bit higher to 110, and I put my y min at 0. And so when I graph this, I got this picture here. So clearly exponential decay is going on here. Now I need to put in Y2, I'm going to put in 10. So I want to know when will the amount of caffeine in the body be less than 10 milligrams. We want to find, once again, we want to find that point of intersection over here. So second trace 5 is intersect. And I'm going to move the cursor really close to that point of intersection, just right on top of it there. And I'm going to press, it says first curve here, I'm going to press enter. It's going to say second curve, I'm going to press enter. It's going to say guess, I'm going to press enter one more time. And my intersection happens at 15.267 hours. 15.267 hours. So T equals 15.267 hours. And it's actually going to be after that time that will be less than 10 milligrams. After 15.267 hours, we will have less than 10 milligrams. You can see I also sketched the graph over here. When will the amount be 0? Well, this is a horizontal asymptote, right? The x-axis is a horizontal asymptote, so theoretically we will never have none. It'll just keep getting closer to 0, but theoretically we will always have a trace amount of caffeine in our system. The x-axis is a horizontal asymptote, and that's the reason why. Okay? Okay, so the second sort of problem we have is a half-life decay problem. We looked at exponential growth and decay, that's our first type. Now we have half-life. The half-life is the amount of time it takes for half of the atoms in a sample to decay. So example 3, a chemical substance will decay by half in 3 hours. So the half-life is called 3 hours. You know, we call that the half-life. It'll be a length of time is 3 hours. Complete the following table for a 200-gram sample. So if I start with 200 grams, in 3 hours, I only have half of it left. 200 times 1/2. I only have 100 grams of the sample left. And then 3 more hours goes by, and I'll have 200 times 1/2 squared, or half of 100. Same thing as 200 times 1/4, 50 grams. After another 3 hours, another half is gone, so 200 times 1/2 to the third is going to be 25 grams. So write a formula for the number of grams left after T hours. Notice this was every 3 hours, and so each time I'm going to take 200 times 1/2, and then I'm going to have T, but that's going to get divided by whatever the half-life is. In this case, my half-life is 3 hours. So that when I put in 3 for T, I'm going to do 1/2 to the first power. When I put in 6 for T, I have 1/2 to the 6 divided by 3, the second power. Okay? So T over 3 here. How much will be left after 10 hours? Well, I know it's less than 25. And let's use the calculator here. I'm going to go to my home screen. And I'm going to say 200 times 1/2. Oops, I want to put that 1/2 in parentheses. 200 times 1/2 to the 10/3. 10 divided by 3 power. And I get 19.843. 19.843 grams will be left. And I did that by 200 times 1/2 to the 10/3 power is approximately 19.843 grams. So in general, my half-life decay formula, A of T, the amount at time T is equal to our A sub 0, our initial amount at time 0, times 1/2 to the T over K power, where T is your time, K is your half-life. And the note here, T and K must be same units of time. If K is in minutes, then T needs to be in minutes. If K is in hours, T needs to be in hours, etc. All right, so the last sort of problem we're going to look at is compound interest. We have, example is $4,000 is invested at an annual rate of 6%, compounded quarterly. Quarterly meaning 4 times per year. Complete the table below if no withdrawals are made. So if I'm investing at 6% 4 times a year, then each time it compounds the interest, I'm only going to get 1/4 of that 6%. Okay? because that's an annual interest rate, and we're doing it 4 times a year, so each time 1/4 of 6%. So for the first payment after 1 quarter, we put it $4,000 is what we're starting with. After 1 quarter, we would have 4,000 times 1 plus that interest rate 0.06 divided by 4 to the first power, and that is $4,060. After 6 months, that's 2 quarters, 4,000 times 1 plus 0.06 over 4 squared, and that gives us $4,120, $4,120.90. 9 months to the third power, 4182.71. After 1 year, that's 4 quarters. 1 plus 0.06 divided by 4 to the 4th power, and that is 4245.45. After 2 years, that will be 8 quarters, 0.06 over 4 to the 8th power, and we will have 45.0597 cents. What you might notice here is that first quarter we made $60. We made a little bit more than $60 during the second quarter, $60.90, and then it went up by a little bit more than that. It went up by a little bit more than $61 over the next time, and then about almost $63 the next time. So it's increasing each time. The amount of interest increases each time, and that's the power of compound interest there. So write a formula for the amount in the account after T years. We'll have 4,000 times 1 plus 0.06 over 4 to the T years, but each year is 4 quarters, so 4 times T. So 1 year, we're doing it to the 4th power, remember. 2 years is 8 quarters. 4 times 2 is 8. So to the 4T power. How much will be in the account after 5 years? So we're going to put in 4,000 times 1 plus 0.06 divided by 4 to the 4 times 5 power. And when we do that, we're going to end up with 5387.42. How much will be in the account after 5 years if the interest is compounded monthly? All right, so if it's monthly, how's our formula going to change? Well, instead of being still 6%, but instead of dividing it by 4, we're going to divide that by 12, because we're going to be spreading out that interest over 12 payments a year instead of 4 payments a year. And then it's going to be 12 times 5 as my power, the number of months times 5. So we'll have 60 times over those 5 years that we're compounding the interest. And that actually gives us $53.95.40. Okay? A little bit more. Notice it's about $8 more if you're compounding monthly versus compounding quarterly. Okay, last problem here. Find the principal needed to have $5,000 after 10 years at 6.5% compounded monthly. All right, I want to end up with $5,000. I don't know what that original amount is. We're going to use P for principal here. Principal is the amount of money you invest at the beginning. I have 1 plus my interest rate is 6.5%, written as a decimal, 0.065. I'm compounding monthly, so I'm going to divide that by 12. And this is after 10 years. So my power here, my exponent, will be monthly 12 times 10 years, 120 compoundings. So I want to solve for P here. So I'm going to put this part right here in the calculator. This is just a number, no variables in there. So I'm going to put that in the calculator. You'll see 1 plus 0.065 divided by 12 to the 12 times 10 power. And I get roughly 1.912, but I'm going to use the exact answer. So I'm going to take 5,000 and I'm going to divide by that number that I have in the calculator. So I'm going to say 5,000 divided by, let me put that down, 5,000 divided by my last answer, second negative sign, A&S tells me it's using the last answer in the calculator, so 5,000 divided by that last answer is 2614.81. So my principal I need should be $2,614.81. If that's what I have right now to invest, and I can get 6.5% compounded monthly, then I should end up with $5,000 after 10 years. In general, compound interest, the formula here, A of t, amount in t years. P, the principal, is your initial investment. That's your A sub 0, so to speak. R is your interest rate. N is the number of times compounded per year. And notice that our exponent here is N times t, the number of times compounded per year times the number of years. So, here's your reward now. What do you get? When you cross a pencil with a hot dog, the answer is an X. Here's your pencil, here's your hot dog. You cross them, you get an X. You're welcome for the laugh.